Okay, in section 1.6, we're going to talk about these transformation rules that you have really been discussing since Algebra 1. You recovered them in Algebra 2, and so we're going to briefly discuss these here in pre-calculus as well. So, first things, a couple definitions. A rigid transformation is one that leaves the size and the shape of the function unchanged. And so that would be, for example, like a translation. If I were to move the graph left, right, up, or down, that would not change the size or the shape of the graph. In addition to that, if I reflect the graph either over the x or the y-axis, that is also not going to change the size or shape of the graph. Now, here's a really fancy word. A non-rigid transformation distorts the shape of a graph. So when we talk about non-rigid transformations, that is our vertical or horizontal stretches and our shrinks. Okay, so we're going to talk about translations first, just as a reminder. So when I have a horizontal translation, that is whenever I have a constant being added or subtracted on the inside of the function. And that's going to be a common theme in this lesson, is that horizontal happens on the inside of the function. So for example, if I have y equals f of x minus c, notice that that minus c is on the inside, and that translates the function to the right c units. And that's perhaps a little backwards from how we would naturally think. A lot of the times when we think negative, we think to the left, but a minus c actually moves the graph to the right. So just a quick example, if you had the square root of x minus 4, that is a translation to the right 4. Secondly, if you have f of x plus c on the inside, that translates the graph to the left c units because it's on the inside and it is plus. And so just a basic example, if you had the absolute value of x plus 2, notice that the plus 2 is on the inside of the absolute value bars, and so this function would be shifted to the left 2. Okay, vertical happens outside the function, and it behaves the way you would typically think, meaning if you see minus, that means down, plus means up. And so here you notice the minus c is outside of the function. It's affecting the y value, f of x, whereas up here, the plus c is affecting the x value, so you can kind of think about it in those terms as well. And so just a quick example would be like g of x is equal to the square root of x minus 2, and so you see the minus 2 is outside the radical, therefore that is a translation down 2. And then if I want to go up 2, that means that the constant is on the outside of the function and it is positive. So absolute value of x plus 4, that would be a function that got translated up 4. For reflections, what you're looking for is a negative. And so if you see a negative on the outside of the function, that's going to be a reflection across the x-axis, and it's going to change the sign of the y values. And the reason for that, the way you can think about it is, this negative is being applied to f of x, which of course is just another way of saying y. And so really what this equation, y equals negative x, is saying is it's saying y equals negative y, which just means take the y coordinate and replace it with the opposite y coordinate. And so when you do that, I'm just going to put a here since this is point A. When you do that, let's just say that we take the parent square root function. When you reflect across the x-axis, that means that you are changing the y-coordinates. All of the x-coordinates are going to stay the same. I'm going to try to use a pen and not a highlighter here. So the x-coordinates are going to stay the same, and the y values are going to be what changes. And so if this function here is the square root of x, then the one that I drew in red is going to be the opposite of the square root of x, or negative square root of x. Now for letter B, when I wrote reflect across the y-axis, that means the negative is occurring on the inside of the function, so it's changing the x-coordinate because you can see the negative is in front of the x. So again, if I have this parent square root graph and I reflect it over the y-axis, it's going to look like this. The x-coordinates are going to change, but it's going to have all of the same y-coordinates, and so this is going to be the equation square root of negative x if this is the square root of x. So negative on the outside is a reflection across the x-axis. It changes the y values, and a reflection over the y-axis means that the negative is on the inside of the function, and in that case the value of the x is going to change sign. All right, for stretches and shrinks, let's talk about vertical first. Notice where that c value is for vertical, that it's on the outside of the function. So that lines up with what we've been saying so far, that outside means vertical. If the c value is greater than 1, then that is a vertical stretch, and that would sort of line up with how you would intuitively think about that. So just as an example, if I have y is equal to 2 times the square root of x, then this is a vertical stretch by a factor of 2. If the c value is between 0 and 1, then that is a vertical shrink. So for example, if I had, let's just say 1/3 of the absolute value of x, then that is going to be a vertical shrink by a factor of 1/3. So vertical behaves exactly like you would expect it to. If it's a 2, it's a stretch. If it's a 1/3, it's a shrink. That makes sense to us. Horizontal is the one that is backward. So first of all, notice where this c is. It is located on the inside of the function, and so that's how you know that it's going to be horizontal. And if the c value is bigger than 1, that is actually a horizontal shrink, and it's a horizontal shrink by a factor of 1 over c, or the reciprocal of that c. And so, for example, if I have y is equal to the square root of 2x, notice where the 2 is, it's on the inside of the function, and so therefore this is a horizontal shrink because that number is larger than 1, and it is a shrink horizontally by 1 divided by 2. Okay. Secondly, if c is between 0 and 1 and it's on the inside part of the function, that is actually a horizontal stretch, again by a factor of 1 over c. So for example, if I have y is equal to, let's just say 1/3 x squared, then I notice that the 1/3 is on the inside, and so that's going to tell me that it's horizontal. The fact that that number is smaller than 1 tells me that it's going to be a stretch, and it's going to be a stretch by the reciprocal of 1/3, which of course would be 3. Okay, so as we've been saying, the general rule is that if the number is on the inside of the function, that is affecting the x's, and it is opposite of the way you would normally think. So for example, if you have, again, absolute value of 1/3 x, that 1/3 is on the inside, it's smaller than 1, but that actually means it's a stretch because it's horizontal, because it's on the inside, and it messes with the x values. If it's on the outside, that affects the y's, and it behaves the same way that you would think about it. So for example, if you have absolute value of x and then plus 2, that plus 2 is on the outside, and so that means that your function is going to go up, because plus we usually associate as going up. And finally, the order matters. So we are always going to do our stretches and our shrinks first, then reflect over the x-axis, then translate right, left, up, or down, and then finally reflect over the y-axis. So make sure that you go in that order when you're applying transformations.